Okay, cool. All right, I'm going to get started. So the goal for this lecture today is to go further into the theory of observables in a quantum field theory. I think it'll touch on a lot of things that has already been mentioned in talk so far, and will certainly be used. I will certainly use it, and I think David will as well in the talks going forward. So I'm going to start with quantum observables, which we sort of ended with last time in a zero-dimensional context, where I tried to explain this idea that a zero-dimensional quantum field theory, at least formulated in this in my sort of derived sense, recovered some ideas in calculus, namely integration against measures of the sort of type we care about in QFT. And sort of in this zero-dimensional situation are sort of ansatz for the classical observables. We're given as functions on some -1 shifted symplectic space, which typically in many of the examples we care about are actually of this form. So it's this is sort of the basic example of a shifted symplectic manifold. And possibly there is some action functional, like this. And at the quantum level, so this complex knew nothing about integration. It was only after we quantized that we could start talking about integration. And what that sort of resulted in was a deformation of this complex, and a deformation really in the style of deformation quantization. And I'll make that analogy again in a minute. So this looked like functions on t star -1 of x. Now adjoin, so I'm always working sort of perturbatively, so I'm working with a formal parameter h bar. And now the complex here at the quantum level, like I said, is deformed. So it's deformed by some operator called the BV Laplacian. And it was this operator here that more or less corresponded to the de Rham operator in finite dimensions. And so more geometrically, if x is just an ordinary manifold here, I can identify functions as a object on x in terms of polyvector fields, some standard geometric objects on x. And this operator here was nothing but the divergence operator. In identifying polyvector fields with de Rham forms, I had to choose a volume element here, and I'm taking the divergence with respect to that same volume element. Okay.
Some kind of first derivative in h bar.
Yeah, so exactly. So Dan is asking how this is related to the symplectic form, I believe. And that's a really good question. So in fact, it's a second order differential operator acting on this complex here, acting on polyvector fields, if you like. And its symbol is exactly the symplectic form. So it's restricted to sim2, if you like, inside of here is exactly just the symplectic form on quadratic elements. Yeah, thanks. Importantly, and I want to emphasize this again in a minute, this operator here is not a derivation. So the de Rham operator is a derivation, but there's this weird cohomological shift that's happening when I identify this divergence operator with the de Rham operator. So the moral of the story is then that, well, this thing was a nice commutative algebra. In fact, it was a commutative algebra with a bracket that I'm writing here. It's a shifted bracket. This deformed object at the quantum level is no longer even an algebra in a derived sense. It's not a DG algebra anymore, because this operator here is not a derivation. So that's part of the structure that's sort of being deformed here, just like in deformation quantization. Here we're deforming away from a commutative algebra to some vector space. This is just some vector space now. It has some more structure. It has the structure of what's called a BV algebra. That's where the name comes from. This thing is what's called a BV algebra, which I don't want to get into the details of. I'll probably say something about related objects in a minute. But this sort of object actually already appeared in some of the lectures already. s-
The symbol is symplectic form.
inverse. Thanks. Thanks. It's the inverse of the symplectic form.
You do this with a plus one structure.
You could, yeah. That's right. Yeah. Yeah, so with an odd Poisson structure, the thing you would have to check is the quantum master equation. That is not going to be guaranteed anymore. So for example, if the Poisson structure, here we're just working in a sort of a linear context, the Poisson structure could have some arbitrary order. And in general, there's going to be an obstruction for the Laplacian associated to a Poisson structure to solve the master equation. So you have to check that, but you could attempt to define it for an arbitrary Poisson structure. Okay. So yeah, what I want to think about this then is, as I was getting at, is as a -1 shifted Poisson algebra. Sorry, this is a -1 shifted Poisson algebra. And we're deforming to something called BV algebra. So that's the analog of deformation quantization.
Quantization would take place, so to speak, for dimension one, that would be an even symplectic form. But you're saying when I deform in that context, they don't get an algebra, ordinary algebra?
You don't get an ordinary algebra. So the way that deformation quantization, so the way that deformation, and I'll say this in an example later, the way that deformation quantization fits into this is really you have to take into account locality. So this is all about a zero-dimensional field theory. I think about this as sort of being like the universal sort of object you have in a quantum field theory. Locality will come along for the ride to tell me that I have some additional algebraic structure. So what I'm going to say in a second is that you can, by taking into account locality, you get local versions of both of these objects here. So at the classical level, we already talked about what that local object was. So in field theory, obs classical is a cosheaf of -1 shifted Poisson algebras on spacetime. So the cosheaf property is just induced from the cosheaf property that I have on my fields. So this is dual to fields. Really, it's like functionals on the fields. It's a good thought exercise to think about why this is actually a cosheaf. The key point is that functions is monoidal to commutative algebras, so therefore it preserves colimits. And the cosheaf condition that you had before is preserved upon taking functions. This is a nice cosheaf of algebras. Now, what happens when we deform, now there's a lot of subtleties that go on here, which I talked a little bit about last time. So in a field theoretic context, you have to really work hard to make sense of both of these objects here. So in general, there's this problem of UV divergences that we have to handle in defining the quantum effective action. So this uses renormalization, some method of renormalization. And also there's a renormalization that has to happen with this BV Laplacian as well. Well, just from what Greg said, the symbol is the inverse to the symplectic form. That's a distributional object. And if I want to act on other distributional objects, I have to resolve somehow. I can't just do that. So there's two sorts of UV divergences that come in. I'm not going to pay much attention to all that goes into doing that anymore. That was the purpose of last lecture. But the moral of the story is that this is both no longer a commutative algebra. That was clear even in a zero-dimensional case. And it's no longer a cosheaf. So we've broken both of those structures. So what is the residual structure then we have around in quantum observables anymore?
Sorry. I think you said this last time, but
Yeah.
these observables are just functions of the classical solution.
That's right. Yeah. So this is like a particular model for that, but whatever, if you don't like this model, what you should be thinking is that I'm just looking at functions on the equations of motion. Yeah, so I'm like prescribing some efficient models for this object as a particular -1 shifted symplectic object, but in general, you just have, it always has a -1 shifted symplectic structure. It's so the issue is that it's not, it actually these are actually the same reasons. So the point is that the forgetful functor from commutative algebras to vector spaces does not preserve colimits. So this thing is not, even this thing is not a cosheaf of vector spaces. It's a cosheaf of commutative algebras. So because I don't have a commutative algebra structure anymore, it doesn't even make sense to talk about algebra. It just fails to be a cosheaf of vector spaces.
Are you saying it's not even a cosheaf of sets?
It's not even a cosheaf of sets, no. It's a pre-cosheaf for sure. Yeah, we always have that. Yeah. Sorry, I'm talking about gluing. I'm specifically talking about gluing. Yeah. Thank you. Yeah. Okay. Yeah, so for me, when I say locality, I'm sort of I'm sort of not making the distinction so much about the fact that it means for me both that you can sort of restrict yourself to some open, but also that you can build solutions based on its value in small opens. Okay. So the resulting structure is that of a factorization algebra. That's the theorem.
Locality.
That's right. So that's what wants to basically deform this structure here. So it's a solution to both problems, both the sort of, well, I guess I should say effectively here, essentially here, factorization algebras in BV algebras is really what I'm thinking about. But let me just work with vector spaces. Let me not talk about BV anymore for a minute. So what is a factorization algebra? So a factorization algebra is an assignment to every open set. So here M is now space-time. I have a object. So this makes sense in any category, which is symmetric monoidal. You can take this just to be vector spaces. In all the examples I talk about, I have chain complexes. You could use spaces, any your favorite symmetric monoidal category. This is an object of C. And also, not only this, if I have a now disjoint union of open sets sitting inside of M, what sort of structure do I get out? I get a map from the I-fold tensor product of the object F evaluated on each of these open sets. And sorry, let me something a little more general. If these sit inside of some other open set V, so this is another open set inside of M, then I get structure maps of this kind. So this is the data of a factorization algebra. The data is that for every disjoint union of open sets sitting inside of some bigger open set, I have some structure maps here. And in the general case where I'm not assuming anything about topological, I'm not assuming that I have in any sense a topological factorization algebra, which means here it's essentially a locally constant property of the resulting pre-cosheaf. That's the one way to formulate topological here. I'll say that again later on. This is totally more general than that. So this works in any Riemannian context. This is a general procedure or a general definition. And there's some axioms that we have to satisfy. So the first is sort of an operatic axiom. So in fact, one way to sort of phrase this definition in a sort of short way is to say that we're studying algebras over a particular operad. Really, it's a colored operad built from the manifold M. And what that says is that basically these structure maps satisfy some associativity. And you can sort of hopefully imagine what I mean. I'll just draw a picture. If I have some open sets, which are disjoint sitting inside of some big open set here, and maybe possibly I have some smaller open sets, which even sit inside those open sets there, I get a ton of structure maps here. And I potentially have two different ways of going from the smallest open sets to the biggest open set. And I want those ways to be equivalent. So that's what I mean by associativity here. And then also, there is a gluing condition. So this is the second bit of locality. There's a gluing condition here, which I do not want to write the axioms down for, but I want to just remark that it's distinct from being a cosheaf in the ordinary topology that I have on a manifold. This gluing means that F is a cosheaf with respect to some other topology. It's what's called the Weiss topology. And this is a massive topology. So just to give you a flavor, a cover in this topology, what does it look like? Well, if I'm given manifold M, I have a cover if and only if for every finite collection of points in my manifold, I can find an open set in that cover, which contains all those points. So that's really massive. This is not one of these ordinary topologies we're used to studying. So there's, you need many more open sets, exactly, and to have a cover in this sense, yeah. So it's much finer, you want to say it that way. This is closely related to another description of factorization algebra. So here I'm following the approach of Costello and William, which makes sense, which is really nice for me because it makes sense in a C infinity category. I'm here really talking about a manifold M. This Weiss topology is very closely related to the Rand space, which is another way to talk about factorization algebras, which I don't want to get into. The Rand space. So it's essentially the space of all finite number of points in our space. And this topology here is connected basically to the topology on the. Yes, those are the axioms. I don't know. I don't know. So what's sort of important, which I won't say anything about, is that we really have we're really studying this thing on Riemannian manifolds. The axioms have to be changed or sort of thought about seriously in the Lorentzian context, and people like Owen William and Kasia Resner are sort of studying the notion of a factorization algebra in Lorentzian context as well.
Yeah, I think they would say something.
Mm-hmm. I can write the names down if you want. So relating to other, not Kevin Costello, no, the other author of the book, Owen William, and his collaborator, Kasia Resner. Can anyone spell Resner? J-S-Z, anyone? Okay. Yeah, so they make some, I don't know exactly the models that you're talking about, sorry, but they do make some touch with other approaches to algebraic quantum field theory.
When does the Riemannian or otherwise?
It's not clear at all. So it's about producing examples. So it's hard to produce examples of one of these factorization algebras. And a non-Riemannian signature. It's not built in at all to these axioms here. It's about producing examples. So I just don't know if there's no examples in the Lorentzian context that fit this axiomatic framework. That's right. Yeah, it's a sort of a technical. Okay. So before moving on to David said that I really like local operators, which is very true, which is I'm going to spend most of the lecture on after this. But let me sort of advertise that this notion of a factorization algebra really makes contact with more than just local operators. So let me do Mignon's favorite example, abelian Chern-Simons theory. And I'm just going to work on R3. So all we have is, and I'm going to choose the trivial connection and work around that. So I'm looking at my field is just a one form, and my action is just ADA. So there's a gauge symmetry here, meaning there's a symmetry of this action, which I would like to remember. And here, that's just encoded by the de Rham operator. So for any function C, this action is left invariant under this transformation here. This is a abelian gauge transformation. That means that in the sort of taking this seriously in the BV formalism, the sort of fields.
Boundary.
Yeah, so I'm going to take that boundary condition, which you need, of course, here to make sense of. You'll see what I choose in a minute, how I do that. Yeah. So in the BV formalism, this means is that the fields are not just one forms, but actually consist of the entire de Rham complex. And there's a, I'm not writing this as a shifted cotangent bundle as I did before, but it does have a shifted symplectic structure, at least when you take into account these boundary conditions. So that shifted symplectic structure is exactly A wedge A prime integrated over R3. So here now A stands for, let me just write it as alpha to not be confusing. So alpha are just elements inside of this cochain complex. This is really a sheaf of cochain complexes, of course. And the symplectic pairing, the odd symplectic pairing is wedging and integrating. And this, of course, does not make sense unless I assume alpha satisfies some boundary condition. The one I'll choose here is just to demand that alpha have compact support. What's really important, though, is that this pairing is really happening at the level of vector bundles. That's really the key thing. There's a non-degenerate shifted pairing at the level of vector bundles.
Do you really get isomorphism from the tangent to the shift of this dual?
No. So the dual has to involve compactly supported sections. So you really should take the Serre dual. So here there's an isomorphism between. So this pairing just tells me there's an isomorphism between the dual of this and distributional dual shifted by 2.
Right, that's what I was okay, so why is this what?
So I lied when I said this is shifted symplectic. It's not.
That's fine.
Yeah, it's not. It's not shifted symplectic.
So the formally.
Formally it is, because at the level of vector bundles, there is a pairing, which is of the right degree, and that's all I need. I need that pairing. That's what I need. Yeah. So for example, this is enough to obtain a shifted Poisson algebra at the level of classical observables. That's all I needed.
This thing here, I could do it with 600.
So when no, it's a shifted cotangent bundle. So I mean, this pairing tells you how to think about it as a shifted cotangent bundle.
Oh, I see it.
Yeah. But I didn't have to present it in that way. So the point that I was making with factorization algebras before, they make sense on an arbitrary open set. So that's clearly going to handle more than just point operators, which could be encoded by taking a very small open set around a point. So in particular, what I could do is I could take a knot inside of R3, and I'll draw it like David did. Then associated to a knot, I have an observable. I have an element of the factorization algebra evaluated on any tubular neighborhood of this knot. So let me take that tubular neighborhood to be something like this. So call that tubular neighborhood T. Then I obtain an observable on T, defined by sending a gauge field to its integral along. So this is a linear observable. Okay. Now, sorry, let me write this up here. Now, there's a structure map here where I can embed the tubular neighborhood into all of R3. And I claim that in cohomology, at least, this observable simply goes to 0 inside of there. So this is a statement in cohomology. Yes. Yep. So this is just secretly the statement of Poincare duality on R3. So the point is that this is a linear observable. One way to think about it as being dual to fields. And in fact, when you do that, this lives in omega 2 bar compact support on T. Okay. And then all of this embedding is doing is it embedding this distributional object here into the same distributional object, but now with T replaced by R3. So these are both inside of here. These are the linear observables. That's the linear observables. So I'm just saying, in cohomology, I don't have any interesting classes inside of here. That's the Poincare lemma. So that means that on R3, O of k is equal to d rho for some other observable. So some other linear observable. Oh, it's just linear in the field. So yeah. So when I say observables, I always mean like polynomials on the fields or power series on the fields. Yeah. Not doing anything interesting analytically in that sense. Yeah, yeah, definitely. So it's at least very well behaved when your complex is elliptic. So the de Rham complex is elliptic. Yeah, ellipticity is just a local thing, right? So great. So at least when I view this not observable inside of the full cohomology, the global observables, here the global meaning on all of R3, it's trivializable. So now if I take two knots, K and K prime inside of R3, then I can compute the quantum differential. So here, bracketing with S is simply just the de Rham operator. That's the kinetic part of the action. So it's very simple. So this is the quantum differential. and I can compute it on something like rho times OK prime. Okay, so I'm computing it on this specific quadratic observable.
So what was K and not, or what?
K is a knot. K is a knot. And now K prime is, yes,
You said it was triple plus.
yes, yeah, yeah. K is just a knot in R3, yeah. So now what I'm doing is I'm fixing two knots, K and K prime. It still is trivializable, yeah, but I want to make a statement just about knots for a minute, yeah. And just to point out, so this observable here is cohomologically degree 0. A is a field, an actual physical field. There's no interesting degree here. So of course, rho then would be degree -1. It's a homotopy. So this quadratic observable is also of degree -1. It's like a homotopy. And in fact, what I'm going to say is that this provides a homotopy between the product, which is here the factorization product. This is like the 2-point function that I just told you factorization algebras give you. So that's what happens when the de Rham differential hits the first piece here. That is a derivation. This operator is closed for the de Rham differential. So I get this operator out, this quadratic operator out. And then I can apply the BV Laplacian, which is a second order differential operator. So that's going to land me in constants here. And as Dan said before, the Laplacian here is essentially just the inverse to the symplectic. So what that is just the integral then of rho times OK prime. When I'm writing it like this is I'm just meant to, all I'm writing is like a distributional pairing here. So rho here is a compactly supported 1 form because compactly supported. So sorry, I should have said distributional. I'm thinking about it in the distributional sense here. Yeah, this is a number. So to make this argument precise, I need to choose some resolutions, and I'm not doing that because there's a problem already here. I'm multiplying distributions together. But by ellipticity, you can smear those out to view these as actual compactly supported forms. And this will be a compactly supported 1 form, and this will be a compactly supported 2 form. So this is something you can integrate over R3. And it's a great exercise done in the book of Owen and Kevin to show that this thing exactly encodes the linking number. This is exactly the linking number.
But I think what you're saying is these are the ellipticity, these are actually infinite.
Yeah, definitely. Yeah, that's right. So the sort of outcome, the consequence of this is that the factorization product, or at least its cohomology class, is exactly the linking number. This is a quadratic observable, and this is a constant observable. So we have there's some interesting relation inside of the cohomology of quantum observables here. So I only have a abelian Chern-Simons here. I'm only looking at abelian Chern-Simons here. I'm doing, yeah, perturbative Chern-Simons. Yeah. So I'm just working on R3 here. There's no global.
So, for example, I've looked out myself and I'm very that if I take the OPE of 2 Wilson lines in abelian Chern-Simons theory, the OPE depends on the framing. Relative framing.
Okay, I don't have, I don't.
That should be showing up.
I don't see it at all here because this differential is just, so this thing just exists. There's no anomaly at all. I have a well-defined factorization algebra. There's no reference to any sort of framing. So I'm curious to see how it should pop up here, or why it doesn't pop up here. I'm curious. I don't know.
Is this space of rows somehow related to space?
No, I don't think so. No, it doesn't depend on the choice. But maybe, yeah. I haven't.
Some homology class that is
This linking number, this thing represents the linking number for any choice of row.
So the way, okay, if I change the framing for not, that's essentially an integer.
Yeah, yeah.
So, the change, if I have two operators with different frames, the change of these, I'm thinking of compact gauge group.
Okay.
But still, in R3, abelian Chern-Simons level K is something like exponential 2 pi I times that integer squared over K. It's something of that nature. So I would need to know what is the level.
Yeah, I didn't write that actually. Sorry. There was an H bar here. Thanks.
Okay, so you better make fun.
sorry.
So there should be a thing.
But I didn't quite understand.
This is only has some time.
You're saying the linking number itself becomes an framing?
No, he's saying the operator
I'm saying
product.
the operator's definition of the Wilson-Line operator, I'm pretty sure. The definition of the operator of abelian Chern-Simons is not, doesn't just depend on loop, not link. It depends on the framing of that, but an interpreter.
I'm going to move on because I wanted to get to other things. Yeah. I would love to talk more. I'm going to move on though.
Formula, you said OK prime with brackets. What is that?
Oh, this is in cohomology. That's what I meant. So here I'm viewing this as a homotopy. So it says that the right-hand side is cohomologically trivial. This thing represents the factorization product inside of the global observables. And it's equivalent to this number here. Yeah.
Plus or minus.
Yeah.
Okay.
Yeah. Okay. Now I'm going to move on to local observables. So the local observables, we've mostly in all the lectures, we only encountered topological field theories more or less. The local observables in a topological field theory have a nice structure, that of an EN algebra, which I'll move on to now. So same setup as before. So C is any symmetric monadal category. An EN algebra is an object in this category, together with a collection of operations, A tensor K to A for every K, or rather for every collection of K disjoint disks. In R to the N. What's up? So dis here means let me just write them as I'm thinking about them as like polydisks, say. So just boxes for now. Just say that.
But I shouldn't think of them as balls.
You can think about that as balls too. That's fine. Yeah. Yeah, so I mean, really, so all it depends about is the points, and you could just think about in this geometric picture, just some small balls around the points. So essentially, all of the operations here are just parameterized by the unordered configuration space, or the ordered configuration space of k points for all k. So the way I'm writing this looks very similar to the structure I had before. And this is a theorem of Jacob-Lurie that locally constant factorization algebras on R to the n are the same as these objects here, these En algebras. And this can be made precise even in the model of factorization algebras that I gave before. So I didn't say explicitly what locally constant meant, but this is just about the underlying pre-Cauchy of vector spaces. So it's just saying that for every embedding of balls I have in my manifold, the factorization structure map, the one area factorization structure map is an isomorphism, or really a quasi-isomorphism if you're working with cochain complexes. So that's what locally constant means here. And that's why in the world of En algebras, I can really think about the operations as being parameterized by basically just points. It doesn't depend on the size of the disk at all. It's a great definition of the En algebra, not the original one, but yeah, it's a great definition. Yeah, there's just a little bit of work. Like I define this as an algebra over a colored operad. This is an algebra over an operad. Like you have to. They're slightly different. Morally, this is just a definition. And in particular, when n is 1, what this says is that E1 algebras, or rather, this is not a consequence of this. This is totally independent. But just as an example, E1 algebras are equivalent to the category of associative algebras. And really in this infinity categorical setting, I should probably say the word A infinity here, or DG associative algebras. They're all inside of here. Totally fine for now, just to think about associative algebras. So as an example of one of these objects produced from a topological one-dimensional field theory, well, there's a very basic one called topological quantum mechanics. In the BV formalism, this has been sort of explicated by C. Lee and his collaborators, many other people. Of course, this has been around for a long, long time. I'm just saying the sort of work that connects this to factorization algebras most immediately. But here, all we're studying is a map from R to a symplectic manifold. So now this is actually a symplectic manifold. And the corresponding factorization algebra of observables here turned out to be exactly the deformation quantization of X. And this isomorphism depends on some moduli parameters. So in general, you have some choices in here because I'm doing something perturbative. Yes, yeah, in the sense of Kontsevich, yeah. But the sort of moral of this isomorphism is that factorization algebras plus BV quantization in the one-dimensional setting exactly returns deformation quantization. So this analogy I was making is not much of an analogy. It's really a generalization.
The deformation quantization. You mean the exact one with evaluation theory?
Yes, yes. So this is, so you have one of these for any sort of modulus omega, which is some H bar series of two forms on your manifold X. you have the exact same moduli parameters in studying the BV quantization here, and those parameters just match up exactly. Yeah. You could take this to be zero, and you see there's the usual Moyal product. Okay, so sort of more generally, as I said before, I'm going to leave this definition up for a minute. The K-area operations in a general EN algebra are parametrized exactly by the configuration space of K points in an Rn. Okay. So as a special case here, if I'm just thinking about sort of strict algebras, what I should really be looking at is the two-area operations. So what that tells me is that the two-area, the products, the two-area products are equivalent to conf 2 Rn, which is homotopy equivalent to Rn minus 1, which is equivalent to the n minus 1 sphere. So the two-area operations in an EN algebra, at least in cohomology now, so well, the two-area operations in an EN algebra are parameterized by the n minus 1 sphere. So what that tells me is that in cohomology, I have two operations. At least when n is bigger than 1. So that's a product. So here A is a EN algebra. So I have a product here. So that corresponds to H0 inside of the n minus 1 sphere. So just the constants. But then I also have the volume form on the n minus 1 sphere. Okay. And what that defines for me is something that you should think about as being a bracket. It's a bracket with that carries some cohomological degree. And that degree is the dimension of the sphere. So 1 less the dimension of the EN algebra of n. So A here is any EN algebra, and I'm just sort of, for simplicity, thinking about it as valued in cochain complexes. So then I'm taking the cohomology with respect to the internal differential on the complex, and I'm saying just from the properties of being an algebra over this operad, this cohomology has some algebraic structure, which is much more concrete than thinking about just configurations, or at least for an algebraist, right? This is much more concrete than thinking about some operations parameterized by the sphere. So essentially in cohomology, I just have two operations. Turns out this thing's always commutative, this product here. This is this idea that David mentioned the other day, that if I'm in dimension bigger than 1, I can move disks past each other, no problem. That's what's giving rise to this commutative product here. And this thing behaves like a bracket. So in the sense that it's a Poisson bracket. You would think that, but there's this deep result, which is very mysterious, which is formality, says that when n is bigger than 1, En and Pn are equivalent. Yes. So Pn is the sort of algebras that have these two operations. I haven't defined it yet, but so that these two operations give rise to what's called a Pn algebra.
the homotopy category of the product.
Yes, yeah. It's a very so it's a very hard thing to use in general. Like you do, as David's saying, you lose a lot of information by doing this. It's hard to recover which information you had before. So a PN algebra, I'll just say it in words. I have already started to say it. You have a commutative product that's just ordinary degree 0. You have this shifted bracket, and this this bracket here has to be a biderivation for this product. That's the first thing. And then you also have some graded skew symmetry the way you would on a Poisson bracket, and you have Jacobi as well. So it's really a Poisson algebra, just where the bracket has some strange degree.
But I mean, there are lots of situations where they're very complicated objects, but the category. That's what you think.
Yeah, that's. So when n is 2, this returns the notion of what's called a Gertenhaber algebra, which is very closely related to a BV algebra by this technique that this symbol David wrote on the board, this shearing is what you call it. Yeah. So BV and E2 are very close. They differ up to, the bracket differs by 2 in cohomological degree, but they're very closely related. Let me just do an example called the B model. And just to, because I hope by next time I'm going to say some things about supersymmetry. This is a twist of n equals 2 supersymmetric sigma model. It's one of them. The other one is the A model. And the fields here, just to give a rough idea, they consist of, so this is defined on any oriented 2-manifold sigma. And the target here is just a complex manifold X. Okay. So this is just a 2-manifold, and this is a complex manifold. So yeah, all I need is almost complex, in fact. But let me, yeah, all you need is almost complex to write down the classical action. So that's part of the field. So this is why it sort of has some of that structure of the original sigma model in the sense I'm studying some maps. There's an additional field which comes from supersymmetry in some nice way. This is given as sections over sigma of the pullback of the cotangent bundle of X with values in the cotangent bundle of sigma. And the action is very simple. It's just eta d phi. So it's very closely related to a BF type theory. Or if you like, very closely related to it looks like almost identical to the topological quantum mechanics action too. If we choose a polarization, except the fields have some more interesting structure, of course. So this action is extremely boring.
The fields are pi and
Yes, so the space of fields consists of maps like this together with sections like this.
So,
Yes, and here I'm only writing down the fields in ghost degree 0. There's other odd fields around which I'm not writing. So for example, there's a gauge symmetry here, like an abelian gauge symmetry for eta, because it's a 1 form on sigma, I could shift it by a function. I could shift it by d of a function. So there's like other fermions around that I'm just not writing. Yeah, that's a very important one. Well, I am in this model. Of course, they don't come from. Yeah, that's the interpretation here. Of course, that's not the original interpretation in the supersymmetric model. So it turns out that on a disk, the quantum observables on a small 2 disk here, well, it doesn't, so this model is topological. This theory is topological. It does not depend on any Riemannian structure at all. So the observables form an E2 algebra. This is what the machine of Castello and Goulian would produce for you. is a locally constant two-dimensional factorization algebra, which is equivalent to the data of an E2 algebra. To tell you what the underlying complex of that E2 algebra is, I should evaluate the quantum observables on a 2-disk, and it turns out to be Pauli vector fields on X. And the way to sort of squint and see this, well, the equations of motion, first and foremost, tell me that phi is locally constant. So that's what gives me the function part here in Pauli vector fields. That's what tells me, that's what gives me the X part. So that those are the locally constant parts of phi. Eta, well, it's gauge trivial on a disk because of that gauge symmetry I just told you about that I didn't write down, because I can shift eta by an arbitrary function. Well, it's a function, it's a section of phi star t star. So C here is a section of phi star t star X. But it's an odd section, right? Because it's a ghost. It's like a it imposes a gauge symmetry. That's what the odd directions here are generated by. It's exactly functions on these ghosts right here. And those carry some cohomological degree. Here, C is a ghost, so in operators and observables, it carries cohomological degree 1. So the E2 or P2 structure here is in the form of a bracket, which goes from PVI to PVJ to PVI plus j minus 1. And this is a well-known geometric object called the Schouten bracket. There's a more sort of abstract way to think about this. One way to sort of even realize this model here is as coming from a more basic one-dimensional theory described just by functions on X. And when you do that, you identify the observables with the Hochschild cohomology of O of X, which I'll probably say a little bit about why this sort of object pops up when I say those words. But just to say the E2 structure is exactly the same one that's guaranteed by Deligne's theorem. So O of X is a commutative algebra, in particular an associative algebra. Its Hochschild cohomology has the structure of a Gerstenhaber algebra. It's exactly the same bracket here. That's that Gerstenhaber bracket. I think I'm over time now, so maybe I should stop. It's probably maybe I'll do one more example and then I'll stop. Yeah.
This is the observable in the classical observable.
Sorry, this is yeah, this was classical observables. Let me write this as quantum, and I could put an H bar in here to be perturbative. So this is the underlying vector space of the quantum observables. So here I've taken cohomology. So as a vector space, this happens in deformation quantization as well. As a vector space, the quantum object is basically the same as the classical object. The only thing that's different is the product. Here, that product sort of is manifesting in this bracket. That's what the sort of quantum structure is. Exactly. Yeah, because I've gone to cohomology. Okay. So the last example I want to talk about is, again, going back to Chern-Simons theory. And I learned a lot of this from Kevin Costello, William, and John Francis. So in Chern-Simons theory, now let me just work with perturbative Chern-Simons on, again, R to the 3. with some Lie algebra G. So perturbatively, I just care about the underlying Lie algebra and not the group. Then in this case, the classical observables evaluated on an open set U. Well, these are functions on that BV model for Chern-Simons, which was just the de Rham complex. But in this non-abelian case, I have an interesting differential, which is just given by the Chern-Simons action. So it's given by the bracket, the BV bracket with the Chern-Simons action. Here, the bracket being built from the same wedge and integrate pairing that I have on differential forms. This is also using an invariant form, symmetric form on G, just to write down the Chern-Simons action, of course. So I have a level. That's the level. And it turns out this thing is not just equivalent, it's isomorphic to what's called the Lie algebra cohomology of this DG Lie algebra, obtained by tensoring the Lie algebra G with the commutative DG algebra of de Rham forms, here supported on U. So this is a commutative algebra, that's a Lie algebra, this is a DG Lie algebra. This bracketing with the classical Chern-Simons action is exactly what's called the Chevalley-Eilenberg differential. So this is really the Chevalley-Eilenberg model for Lie algebra cohomology of this DG Lie algebra. That's what pops out of classical observables. So in particular, when U is just a disk, a small disk, this thing is quasi-isomorphic by Poincaré lemma to the Lie algebra cohomology just of G. Or really, it's Chevalley-Eilenberg complex. So in physics, of course, one would say there's no interesting local operators in Chern-Simons, and this is consistent with that in the sense that there's no interesting operators of cohomological degree 0 here. They're all in positive cohomological degree, coming from the fact that Chern-Simons has a large gauge symmetry by G. So when we quantize, we get some deformation of this object. And it's a deformation as an E3 algebra. So before, right, this thing was a commutative algebra. We expected that. When I deform by applying quantization, I obtain an E3 algebra, which I'm just going to sort of denote by this H bar here. That's the only difference in using notation. I'm not going to describe this explicitly. I'm just saying this is what pops out of quantization. But I want to extract some interesting structure out of this. So if I look at E3 algebras, well, there's a nice result in the theory of EN algebras called additivity. And what that says is that to understand an EN algebra, I might as well just understand n independent E1 algebras, structures on the same object. So what that tells me is that I can view, that's called Dunn additivity, Dunn-Lurie additivity. So that means is I can view an E3 algebra as an E2 algebra inside of E1 algebras. Okay. Now, to an E1 algebra, I can associate a category. That category is its category of modules. Let's just say left modules. So I get an E2 algebra object in categories. This is taking the category of left. Yeah, so sorry, I wrote this poorly, sorry. So an E3 algebra is equivalent to a pair of structures, namely E1 algebra structure and an E2 algebra structure. And then the E2 is just going along for the ride here. I'm just taking modules for this underlying E1 structure. So geometrically, what I'm doing is I'm thinking about an interface inside of R3. I've like broken symmetry of R3 to write it as an interface. So I have two pieces now. There's a beautiful story here, which I don't have time to get into, but so E1 algebras were really nice. They were associative algebras. E2 algebras in categories are also very nice. They're the infinity categorical version of a braided monoidal category. And work of Costello, William, and Francis, which is ongoing, identifies this braided monoidal category with exactly modules over the quantum group. Here you see the perturbative or formal version of the quantum group here. That's the only thing you should expect. But I just wanted to give another example of an interesting EN algebra. So here the moral is that the E3 algebra of Chern-Simons theory sort of underlies the quantum group in this sense here. It's a great question as to where line operators are. That happened in the passing from this E1 algebra to its modules. So there's a nice story there, but I didn't have to explicitly say the word line operators here.
Your distinction here.
Yeah, so this only just depends on the Lie algebra. Yeah. So I'm not seeing like that I'm only seeing the sort of formal part of the quantum group.
Wouldn't see it.
Not perturbatively, I don't think. Yeah. I'm gonna stop.